Hello, Mr. Schoening here. I am looking at our lab for this week. We are doing an identifying unknown fluids lab, and we're going to use the concept of density to do this. If you look at our purpose, we see that we are going to devise and conduct a procedure in order to determine the identity of a fluid using density. Hopefully from your chemistry days, you've realized that density is a property of matter, and as long as the matter is a pure substance, then its density should be pretty much constant. Um, we mentioned before about there are factors that can change it a little bit, temperature and stuff like that. But for the most part, for these fluids, we're not going to see that. So what we're going to do is we are going to use a pivot interactive since we are not in class to be able to do this. So what we're going to be looking at today is this equation of density. Again, their symbol for density is this rho symbol equals mass divided by volume. And we want to approach this the way that we would for the AP exam. And that means that we're going to design an experiment that will be able to get density from the measurements that are indicated in this equation. All right, so I'm going to play our video real quick to show you what we're going to see. Note, I'm going to also make sure that you're aware of a few things. I'm looking currently at liquid 2. You can pick liquid 1 or liquid 2. And if I hit play, we'll see what happens here. Now, when we do this, we are going to see, before I begin, that the person here never tears this. So this is reading 84.6 before anything even happens. You have to keep that in mind. We also know, and I don't know exactly 100% why, but there's some kind of liquid already in here. That is not going to matter too much. It's not going to influence the reading that we're looking for. Again, I'm not 100% sure why they did this. Maybe they had the other liquid in here. Really don't know. But not going to matter too much. So what we're going to be able to do in this video when we play it is we are going to see liquid being poured in. This camera here is recording the liquid going in, so we can read the volume at any given moment. Please remember to read the bottom of the curvature on a graduated cylinder. So we're looking for the meniscus, and that's going to be the bottom of the curve. Also, try not to read it while it's sloshing around like this. Try to wait for it to stabilize like that. Read the volume that goes with it. You might want to pause at that moment so it doesn't keep going without you. And as we do in any good experiment, you want to repeat for several trials because who knows, we might have had a bad reading that time, and we want to minimize the error. And the best way to minimize error is to simply use as many trials as possible to see if there was any one trial that was bizarre. All right, so that's going to be how the video plays out. And now what we're going to do is address how you should look at it. The way we're going to look at the labs in this class are going to be a little bit different this year, but I'm hoping that when you do this, you'll start to gain an appreciation for how the labs are created and how the procedures that we wrote last year that were really, really elaborate don't have to be that way. Because what we're really trying to prove in the procedure that we write on the AP exam is that we understood the methodology behind it, not really necessarily how well we wrote English or anything like that. So the first thing that we should do when you're designing an experiment is to take this equation and to write it into slope-intercept form. Now I'm going to go over here to OneNote so we can do this. And I apologize, I don't write very well with a mouse, but I'm still going to use it. And what I would do is I would take my equation, which is rho equals m over v, mass over volume. And this experiment is asking us to determine a density. All right, now the way that we're going to conduct every experiment is that we're going to take the equation. So this time around in the course, what we'll do is we'll tell you the equation that we're trying to model first to kind of give you a little assistance on what you're trying to do. So we're looking for this, and we need to solve that. So the idea here is that let's figure out what this will be. Now, technically speaking, you could just simply take a mass reading, take a volume reading. Both of those were present on the video. Do that ratio, and then see what it was. But again, what we want to do is to minimize error. We don't want to do it one time. We want to use a graphical approach to do that. And what we mean by that is that if we had a graph here, and this graph had a y-axis and an x-axis, that this graph we would somehow be able to generate a line, hopefully a proportional line, but if not, just a straight line would be fine. But we would draw a line, and this line here is going to be the key. We're typically looking for the slope of this line to have some kind of meaning for us. All right, so what we're going to use is when we run this through Desmos, like we've always done, we're going to create that line, and then figure out what we have to do. So what that means then is if we're going to create a line, as it said before, we need to take our equation. I'm going to help you out with this first one, but we need to get it into slope-intercept form. Slope-intercept form is y equals mx plus b. So that means that this equation right here, this big guy right there, this equation needs to be rewritten so it looks this way. Now, in this format, there shouldn't be any fractions. That means that basically we need to get that solved out and isolated. So there's a couple of ways to do this, as long as it's not in fraction form. But what we need to do is get rid of that fraction. So this v can't be here. So I need to take the v and I need to move it to both sides, or multiply it on both sides. That's going to eliminate the v here and get the v on this side. So that means that now I'm going to end up with mass for the m. Now this is, please be careful, this is slope. And this right here is mass. All right, we have to be careful. But what we're doing is we're kind of looking at these two equations at the same time. So we have m will equal rho times v, and then there's no adding terms here, so we're technically going to have a plus 0 here. All right, that's going to make it look like it's in slope-intercept form. If there was a plus or minus anything, well, that number is going to go in the b location where the y-intercept should be. But this is what our equation should roughly look like. So if we do this properly, we would expect to get a graph that does go through the origin. Now, to be honest, I mentioned one thing in the very beginning of the video, that it won't go through if you disregard the comment that I had made earlier. It won't go through the origin. In fact, it will go through a number I had mentioned before. So just be aware of that. So the next thing that we want to do then is take a look at this equation that we have here, because y equals mx plus b is going to be the equation that we're trying to use to make this. But the equation that we're trying to model looks like this. What we want to do is to take a look and see what belongs where. So as you guys set this up, notice that the y is representing the slope in this equation. I'm sorry, not the slope. The y, m looks like slope. The y is actually representing the mass. So that's supposed to be mass. And if we take a look here, the x is representing the volume. Now, if I wrote this the other way, it could have been v rho, and we would say, okay, does the x represent the rho? And it could, but the problem is we don't have any rho measuring devices in the video. So we don't have anything that can measure density, in that video at least. So that means that we don't want to put something that we can't measure on the axis. We want to put something that we can measure. So the v, that's something that is certainly measurable. So this x is going to become v. That will be our volume axis. Now, if that's the case and we put m to replace the y and v to represent the x, the only term that is left is right here. And that is that the slope is equal to density, or rho. So that means that when we do this, if we get ourselves a nice line, that the slope of this graph would be rho. And that's basically how we decide how we do an experiment. So if we look at what we've done now, we've rearranged our equation. We've lined it up in slope-intercept form. We've compared what the y's and the x's are, and we've basically marked them out over here. And now that they're marked out over here, now we know what our procedure should be. If we go back to the procedure and we look at what was asked of us, it says, if we're going to do this experiment, what should be on the x-axis? Well, we just mentioned it. And what should be on the y-axis? Well, we just mentioned it. And when we devise our procedure, we're going to take that information and use it to make our procedure. So that means then that what we need to do is we're going to follow this format. And what we see here in red, we're going to basically highlight and put in words for it. We're going to leave everything else the same way. So the setup blank and blank, that basically means set up what equipment? What are the things that you're going to need? So we look at the video and say set up this, 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 and this. Maybe give a little bit of detail there as to what we mean by set it up. But for example, if this was an old lab, we might say set up a flat and level track in which to place a card upon. And don't leave the et cetera there. That et cetera was because I didn't, if I gave you 17 blanks, some people might think you need to have put 17 things in there. So the et cetera just means add as many of these as you need. And it says here, while keeping constant. So basically in the video, there are things that might be changeable. What are some of the things that you got to make sure from trial to trial isn't different? There's one more obvious thing than others for this video. So there should be something that you should mark as constant. Then what we do is we say, okay, use a what to measure what. So what we now know is that the X and Y are telling us the two measurements that we have to make. So we need to mention, okay, what device is going to be used to measure said variable. So for example, if we were measuring distance, we would say use a meter stick to measure distance. The second one would be what you measure the second thing with. Third thing says, okay, now that you've done that, what are you going to change? So basically, what is going to be your independent variable that you are going to change according to the graph that you made? And then measure the new dependent variable, whatever it is you're going to measure in response to that. All right. Now, in this particular lab, technically either could be independent or dependent, and you might get two different procedures. It'll give you two different answers in terms of what the slope will be, but that slope, when you compare it in the equation, when you solve it out algebraically, for example, what I mean by that is that if you had the V and the M in opposite locations here, well, then what would happen is that the density might not be just density. I believe it would be 1 over density if you wrote the equation in the reverse order. For example, if I isolated this, I'd have 1 over rho times M. That would also be a possibility. But that's not something you probably want to do, and most people won't do it. But that would give me a different number. But algebraically, when I solve out that the slope equals 1 over density and I rearrange it algebraically by taking my slope from Desmos, it would have worked. Anyway, sorry, that's the bell to start the next period. All right, so that's how you set up a procedure. That's the easier way to explain it. Don't, notice that I'm not telling you how you put the data into Desmos. I'm not telling you all the crazy details that sometimes we feel like we need to include, because that's not what the reader wants to know. They just want to know that were you able to figure out what you're testing and how you test it. You'll fill in your data table, mark out the measurement in unit with whatever your measurement was. I left it as this on purpose so that you guys can decide what goes there, because on the AP test they do that. You'll mark in your unit. You'll take 5 data points, and then that's it. So make sure though that you do tell me the liquid that you have, and then use the information that they gave to do this. I do need this equation though, because that's going to be how I determine what you did. All right, so in this lab, it's a pretty quick and simple lab. Collect your data, fill in the numbers, draw this conclusion. If you have any questions, please see me after school or during any kind of planned hours that we could set up, and we'll go from there. Thank you for participating in this lesson. Have a great day.